Okay, so it's right about 9. Any questions before we start? So last time we talked about processing, some of the processing steps. So today we'll continue on doing that, and we'll do what is etching is not listed there. So last time we talked about some of these, and then we talked a few steps, and we stopped right at etching. And one of the steps is it's at the wrong location. This should be pointed to the photolithography. So photolithography is a step that we need to repeat again and again, use it again and again. In every of these other steps, then we need to use photolithography. So that's combined with all the others. So this is an important step. And this is what we illustrated, how you have you use the mask to stop the lights, and then the patterns that you're making is on the surface of the wafer. But you use this step again and again together with other steps. So last time we stopped at etching, and then today we'll continue from etching. And etching, you have etching is a step that you remove some of the materials selectively. So the semiconductor fabrication processes involves steps that you adding materials to the surface, and then involves subtraction method, taking away materials from the surface. So etching is one of the steps that you use to take away materials from the surface. And it's a step that you can selectively take away materials from just the selected spots that you want to take away. So for example, if you want to dig a hole for contact for via, then it allows you to just do it right there and nowhere else. And then you also have other places, other methods for taking away materials, but then you take it away from the whole wafer surface. So etching is a selective removal method. And then last time we said you have a wet etching and dry etching. Wet etching is that you just dip it with many of wafers, you put it in the boat. The wafers are vertically sitting in the boat, and you drop the whole boat into acid water channel, and you put it in it, and then it flows along the channel maybe for an hour, for 2 hours, for some time. And then at the other end, then you take it all out and put it in a deionized water to clean it. So that's how you do your wet etching. Wet etching is very inexpensive. Just put it in the water channel, let it flow. But then it has a few problems. Undercutting, and then it can etch away it will etch away the materials that you want to etch away. But then you may etch away something else nearby. And dry etching is more precise, but then it's more expensive. You can do ion etching, plasma etching. You can do this. So the wet etching is very inexpensive, and it's very widely used for most of the stuff you do. You do this, and so if you want to, so this is a silicon. Let's say you have dioxide. Silicon dioxide, here you want to etch away this part, leave everything else there. So then you put your photoresist layer on it. We talked about photoresist layer before, and then you put a mask on top, and then you shine ultraviolet light to it to expose some of the photoresist, and And then so now after the exposure, and then you process it, and then the photoresist, this part will stay at here to protect this part. You don't want to etching. Similarly here, if you then just this part, then exposed by the light, and then you can take away. Or if so we said there are two types of photoresist. One type is the exposed part becomes soft, and you can take away. The other part is that the exposed part becomes hardened and it stays there. And so if the amount that you want to if the target area you want to protect, then you use the second type. If the target area you want to expose, then you want the first type. So in this case, this target area we want to expose to the etching acid. Then we make the photoresist to be processed away. So now you with this one, then you dip it in the acid water, and then it will etch, and it will etch away. Then this part will gone. Or it doesn't go like this, but then it goes layer by layer, goes gradually down like that. So this is ideally what happens. It looks like that. And but then the acid, when the eat away the materials that you wanted to eat away, it does not necessarily exactly do what you wanted to do. So it will eat away. It will eat away this part you want to eat away, but then it may eat away the mask, the photoresist material here a little bit, and the amount that it eat away on this material versus the intended material, that you call it selectivity. And then you wanted to eat away materials downwards, but then it will also eat away sideways. And that one, the amount that if perfect, then it just eat away vertically, but it will also go sideways. Okay, so if it only goes vertically, you say that you have a nice anisotrophy. I don't know how to pronounce that word. I think it's written on the next anisotrophy. Anisotrophy. Okay, so this then you have an equal to 1. I don't know. There is a mark here. So if you have this is your mask, and then this is the material underneath it. After it eats away, then so this distance, let's say called B, and then now this one will also get so if this one you call the A, then this A over B, this A-B ratio here is defines your selectivity. But then this distance here, let's call this C. This is C. And then this 1 minus C over B, then this you call it anisotropy. So then this one is selectivity. So this is some of the undesired effects. So it can either way the masks, and then this material are also either way this way, and then it goes this way. So ideally, you want your A to be equal to 0, C equal to 0. You only want your B. Okay, that's ideal. And here, then we're talking about the lateral size typically much larger than the vertical size. So then our drawings is exaggerated on the vertical so that it's easier to see. So for dry etching, then you can achieve a very good anisotropy. You get it nearly equal to 1. So then quite vertical. And for wet etching, then it's more likely to get those problems that A not equal to 0 and C not equal to 0. And that A not equal to 0 could have another effect. It could have due to the photomasking processing step. So if your photo mask says that you want this part, but then in the photo when you expose the light, then it may not stop at here exactly. So then the exposed part may go here or may go under. So that could be another part of the area. And once you have your masks after this processing, and then so after development, then you could get a different lens here. And then in the etching part, then some of these would also get etched away by the acid. So from this example, you can see that when you draw something on your design, and then after you fabricate, what you fabricated may not be exactly what you want. Yes, sir.
So based upon this process, since there's at least a decent amount of error,
yes,
does this completely limit how small we can go with transistors based upon the process we have to use?
Yes. So this is why you have all those design rules. In a given process, when they control this, how accurately they can control this, they will figure out, and then they will ask you to leave enough safety margins, and that's why you have all those design rules. Okay, so this is using this one to show that the actual processing steps will not give you exactly what you drew, but then for all the other steps, last time we talked about the ion implantation and diffusion, etc. The area that you draw is going to be different from what you actually get. So you always have those areas, and so then you need to leave enough rooms for safety margins so that you don't get things accidentally overlapped. Any other questions? So so you have the negative photoresistors, and you have the positive photoresistors. One is that you expose the outside, the other one you expose the target side. So you can use either ways. This is, I think we already talked about this, that the vertical dimension compared to horizontal dimension. Yeah, so here is a drawing to showing that now in this particular drawing, you can see that this is assuming that the rate of etching away vertically in all directions is equal. Then originally, suppose it's at here, then it will begin to etch down, and it will also begin to go in that way. So this distance and this distance are about equal. So then this is one situation that it is like that. And so then afterward, after you remove the photoresist material, then the shape that you have is about 45 degrees at the end. Well, this again is ideal drawing. The actual shape here may not be a straight line like this. It is more going to be curved. So the next step is diffusion. Diffusion is when you have two different types of material, you put it together, then the atoms from this side will try to move towards the other side due to gradient. So if you have a concentration gradient, it's going to go from a high concentration to low concentration. So imagine that you have a cup of water and then you put one drop of, very carefully put one drop of ink in it, then you can see the ink gradually spreads out. That process is doing that's diffusion. Well, in the water diffusion, it happens at room temperature, but then for solid silicon, then the atoms does not diffuse much, hardly at all at room temperature. Then what you do is you bake it, put it in a high temperature, 800 C, 900 C, 1000 C, etc. And then at this high temperature, then atoms can diffuse much faster. So last week we talked about deposition and ion implantation. When you do deposition, put some material on the top of the wafer surface, and then you want it to go into it. Then what you do is you put after deposition, you put it in the oven and bake it to 1000 degrees C, and then the deposited atoms will gradually diffuse into the substrate. Similarly, for ion implantation, you do your ion implantation, you like shooting guns, you put the bullets into the material, but then it's crowded somewhere, and then you do diffusion, put it in the oven, and then those concentration, the implanted ions may be concentrated on some locations, but then when you put it in the oven, then it will diffuse, and then it will become more spread around. Okay, so this is diffusion. So diffusion is time and temperature dependent. You can determine how long you are going to bake it, and at what temperature that will control the diffusion rate. So the material itself, the atom size and the density, atom size will and the type of atom will have a diffusion constant, and then the time, then it will just the longer you wait, then the more it will diffuse. And so the temperature that we said that is typically is 800 C to Celsius to 1200 Celsius, but sometimes you want it to go faster, go deeper, then you can even do it at higher, could go to 1400 C. And then for the people also do slightly low so-called low temperature diffusion for this some of these 3D, the newer processes. If you don't want to damage something that you already made, and then you can do so-called lower temperature diffusion, maybe at 400 C. But most of them is in the 800 to 1200 degrees C. And then like was what I said, the impurity source could be deposited onto the surface, and then it will diffuse into it, or could be implanted, and then you let it diffuse. And then you can use the P-type materials, N-type materials for doing the diffusion. So like graphically like this. So if you did CVD, chemical vapor deposition, and then you deposit some silicon materials with some impurities on the top, then you have a top layer there, and then after you bake it, then the top layers will gradually grow down, and then it may diffuse into the desired amount, desired depth. You can control the depth by the temperature and by time. And similarly for implantation, if you implanted on the top some materials, and then after your diffusion, then you can it can go down. With implantation, you can have a controlled small area, whereas the deposition is typically used for larger areas, but the implantation you can control where you have, and then you implant it, and then you can control it. So then you implant just that part, and then you let it diffuse. and then end up you form a shape that is almost like a well there. Any questions on diffusion? So another step that is used is oxidation. Oxide. So the oxide is again is used for separating, for isolation. Oxide, silicon dioxide is an excellent insulator, very good insulator, better than your many of the insulators you have seen. So it's a very good insulator, and then you use it to isolate things, doing electrical isolation, and so it's used throughout the circuit. And oxidation, there are several ways of doing oxidation. You have a thin oxide, a thick oxide, and so you can grow oxide. So one way to make an oxide is that you have your silicon and you just put it, let the silicon surface to be exposed to oxygen, then it will oxidize the silicon, and the oxygen will react and then become silicon dioxide. Okay, so this is a growing oxide. Now, if you have the silicon surface at the original height, after the top layer combines with oxygen, and then the surface height will actually become higher because silicon dioxide is larger than oxide. So then when it combines, then the molecules becomes larger. So it grows upwards. So that's why you call it growth. And for growth, you can grow thin oxide and thick oxide. Thin oxide is like the oxide underneath your gate. You have your transistor, you have the active, and you have a gate. The intersection between the intersection is a thin oxide layer. And that one, like what we said, is in the order of magnitude of 10 nanometers, depends on which process. Maybe 10, 15 nanos, or maybe 5, 6 nanos, right? It's very thin. And then you also have other types of oxide that are used to separate NMOS transistors and PMOS transistors, and those are very thick oxide. And in the order of thickness is in around 1 micron, sub-micron. Okay, half micron, etc. Depends on which process you are in. So here is an example to say that if you want to grow some oxide here, if originally the silicon surface height is here, okay, the silicon oxide, silicon office surface is here, and then is a photo mask, and this part of the silicon exposed to air, to oxygen. And then after you let it grow for a certain amount of time, then the silicon dioxide will grow down, and it will grow also upwards. And so this is ideally, it just goes like that. Just like etching, it doesn't go just ideally like what you want. When you grow this, then the silicon dioxide will also grow sideways. So if we then what will actually happen is that the grown silicon dioxide will have a shape that looks like this. Okay, and after you take away the photoresist material, then what you will end up with is a silicon dioxide material that looks like that. Okay, and in the 0.5 process, that this is typically the silicon dioxide that we use between around the transistors. So this is using the growth, thermal growth. You put your silicon in a high temperature, exposed with oxygen, and then it grows oxide. But you can also do deposition. So in the 0.1, actually I don't know about 0.18 they do shallow or trench or not. But in the smaller feature size processes, then they do this so-called shallow trench isolation. So then if you are going to make PMOS transistors, NMOS transistors, then they will, instead of grow or those locals or the FOX or field oxide, people call it different ways. So instead of grow the locus oxide, then you cut, you etch in an area here, you deposit silicon dioxide material in the trench. So you first etch a shallow trench, and then you deposit, you do a deposition of silicon dioxide into this trench. Now, when you do this, then you have much better control of the vertical edges of the silicon dioxide. So that's one. So the side edges is much better controlled. Okay, it's much better controlled, and then it goes into the other thing. The other thing is that this width here, you can make it much narrower. So you can make it much narrower. Now, if this is the NMOS, this is the PMOS. If you rely on the gold oxide to separate them, then the separation needs to be pretty wide. The reason being that you have the NMOS transistors, you may be in the P well, and the PMOS transistors may be in the N well, and the wells are touch together. Then you are going to have a p-n junction depletion region, and that depletion region can be much wider than the shallow trench width. It can be 10 times wider. So then your area utilization is not good. It's all wasted on this p-n junctions between the P materials and N materials. So we know that the semiconductor processes, the lateral control is very precise, very good. So when we use this one to make this trench, we can control this width very well, and it can be much smaller than the p-n junction depletion region for separating the NMOS and the PMOS transistors. As a result, you can put a lot more higher density of transistors with this shallow trench isolation. And this is after you deposit it. Is there a way we can just turn off this light here? Right? Is this better? Because the color on the screen is a lot worse than the color on the computer. So afterwards, then you can get rid of the masks, and then also you can do polishing to take away all the top oxide. Sitting back there, you probably cannot see. There is this silicon dioxide here. Here is going up higher, and then you have some here. All of these, then you can just take them away, so that anything above that line you can take away. Okay, you can now you have just silicon dioxide here from the shallow trench isolation, and then silicon exposed on the surface again. Then you can put other stuff on it. Any questions on how do we put dioxide on it?
Well, just a question on what the CVD stood for.
Chemical vapor deposition. So we last Friday we said that there are several methods to deposit the materials on the top of the wafer. One is physical deposition, another one is chemical deposition, and a chemical vapor deposition is very widely used. So you just put a chemical gas into the chamber, and you have a wafer sitting there, gas into the chamber at a different temperature or two different gas. Then some chemical reaction happens, and then some solids form, and then it just drops down onto the wafer. So this is the process. Yes.
So a couple of slides ago, you had like this blue layer for the silicon nitride. During the planarization process, where does that go, or does it flat?
So we'll talk about the planarization process. So for example, you can do, it's just like that you use a sandpaper and then sand it away.
So you sand the silicon nitride away, or the pad oxide?
Well, you can control if you do CMP, mechanical polishing, or mechanical planarization. Then this process is just you have a wafer here. It just keeps rubbing and then scrubbing, and then anything on the top it will scrub away.
Okay.
Does it make sense?
Yeah.
So you have on the previous page you have given the height, some different materials, etc. And then you do the CMP. It's non-selectively take away the whole wafer's top, the top part until it goes to that dashed line level. So there's a non-selective anything. It just scrubs away. Any other questions? Yes, sir.
Why don't you get the lateral movement of the oxide like you did in the previous example?
For the shallow trench, so shallow trench is so you first do a cut a trench into it using etching. If you do dry etching, then you can make the slot to be quite vertical. We said wet etching you can go sideways, etc. But then the dry etching you can make it go nearly vertically down. Of course, it's not perfect. It's more slanted on the side, so that trench is more slanted like this. And then so you can cut this trench, and then you do deposition, deposit the silicon dioxide into the trench. Whereas before is that you just expose this area, expose it to oxygen, and then you bake it at a very high temperature. The oxygen and the dioxide, they will just goes wherever it wants to go.
Okay.
But this one is controlled. You first using dry etching, cut a trench in like that, and then you deposit your silicon dioxide into it.
Okay.
So now you have a very nice, nearly very well controlled shape. It's not perfectly vertical down, but slightly tilted. Top side is typically is wider and goes down and like that. Any other questions? So next step we're talking about is epitaxy. So this is another process that you add new materials on the surface. So for this one, then you use deposition. You can use deposition slowly. You can slowly, very gradually deposit material on it, and then also at a raised temperature, and then you deposit silicon on the silicon, and then the substrate silicon is a single crystal substrate. So when you deposit a little bit on it at a certain temperature, then the deposited silicon will try to align the cell with the crystal, and then the crystal structure then grows upwards. So then you get a top layer of this. This one is all deposited, but then you do it in a slow process. So then this is also in crystal structure. Okay, so it becomes the same crystal structure as not the same. It's the crystal structure is continuous, continuous going up. But of course, when you deposit this silicon, you can mix it with some minorities in it. Okay, you can mix it with minorities in it. So the bottom, if this is P type, then we deposit on the top part. You can have P. You can still have P minorities in it. It can be heavier than the substrate. So now you get an epi layer that is P epi layer that is more heavily doped than the substrate. Or you can even do with this one with N materials. So then you get an N-doped epi layer on top of it. Now on the bottom, there is a question here says, why can't diffusion be used to create the same effect as the epi layer?
It's not uniform.
Well, the diffusion is not uniform. The diffusion is typically exponential, so the density is also exponentially goes lower from top to down this one. Diffusion also only gives you a very thin layer, and the taxi. When you do this, you can keep depositing, and then you can have this thickness here to be quite thick. You can let it grow some people let it grow to 10 microns, 20 microns. Whereas your diffusion, you can only diffuse just a little bit. It measures in nanometers instead of microns. You get more uniformity. You get a crystal structure. You can get a very higher, thicker level. The next step is put polysilicon materials, and so the polysilicon is still silicon, but then the polysilicon we have been saying poly for the gate material, and the MOS transistor, the name MOS transistor says that it should be M stands for metal. The gate should be metal. But then in the old days, when they first made the MOS transistors, the gate is metal. But then later on, they find out using polysilicon is much more popular. And so you get this polysilicon is not a single crystal, so it's a polycrystal. So it's not a single crystal structure like the substrate. And as a result, then you get totally different electrical properties out of the silicon, the polysilicon. And then the polysilicon, you can also control how you dope it and how you make it. So like in the 0.5 process that you guys were using last semester, well, you can still use it. Then it has a poly 1 and poly 2. And then these two poly can be of different, slightly different properties. And I don't know in the 0.18 whether there is a high resistance poly or not. Or in the 0.13, many students use the 0.13 process in the Global Foundry. Then you have the high resist. Last time we mentioned that there is a HP, the high resistive poly, and then that property can be very different. Okay, so for your gate poly, you get the poly's conductivity maybe is about 0.1%. You talk about the resistivity is about let's say about 1,000 times worse than the metal. So the metal wise is about you talk about in milli ohms if you have one square shape. But the gate poly, you have roughly speaking about 50 ohms for the same shape, one square shape. You get about 50 ohms. And if you have the high resistivity poly, then you can get a kilo ohm or 2 kilo ohm. So you can have, by controlling the material, you can get use the poly to make a good make a semiconductor, okay, a conductor between metal and the substrate, much more conductive than the silicon, the crystal silicon, but then is much less conductive than the metal. But then you can control its conductivity in a wide range. So graphically, is your single crystal silicon substrate is nice, uniform. All the atoms are in a nice array. Okay, in a horizontal is like a lattice. Okay, it's a very nice lattice array. But for the polysilicon, then is more randomly shaped. So the next step that we're going to talk about is related to, I guess, some of the questions. Her question is about how you do the planarization. So the planarization is CMP, chemical mechanical planarization, or CMP. Some people say that it stands for chemical mechanical planarization. Some people say it stands for chemical mechanical polishing. Either way is that you made the wafer, you have your wafer, you process the different steps. Okay, you put something on it, and then the top surface is not flat, and then you want to move away, get rid of the top material, and then you will just do this CMP. You have this wafer, and then you have this disk that is just turning, and then you may have multiple of these, just spinning, turning, rubbing, and then the wafer itself is also turning and rubbing, etc. So now it's just like a sandpaper. It's like you're doing using a sandpaper polishing the surface. So then the things on the top surface, then you just scrub them away. Okay. After you're done with this, then now it becomes mirror-like, very flat and very smooth on the top. And then you can do another step of adding materials. So this CVD is a step. CMP is a step that you also use again and again. So after you put some material on it, it's non-smooth, then now you do a CMP. You can do CMP to polish it, and then you are ready to do the next step. Any questions on this? So the next is about contacts and interconnect. So contacts are being used to make a connection between different layers. So originally near the silicon wafer at a very lower level, you have your silicon, the silicon substrate itself, and you have the N wells, and you have the P wells, the N diffusion, the N active, P active, those areas. Then you need to make connections to the metal 1 level. So then you make your contacts so that they are connected to the metal 1. And after metal 1, then you may need to send the signals to other places. Then you use other metals to route the signals to other places. Okay, so then So you have people to use the name context and the vias. So from the lower levels, from the substrate material, from the well material, from the inactive pH diffusion source and drain area, from the gate party etc. to metal one. Then you many people call this context. Okay, between the silicon material to metal one, you call them contacts. After you go to metal one, and then from metal one, if you need to send it to long distance, you may need to go to metal 2, and metal 3, and metal 4, metal 5, etc. You go to so many different, when you go from one metal layer to another metal layer, the intersection, this is metal 1, this is metal 2. They are at a different height on different floors. If you think of the building, it's like so all the silicon is on the ground floor, and then you have your metal 1 is on the first floor, and the metal 2 is your second floor, etc. So they are at a different height. From the ground floor to the metal 1, you use your contacts, and then from floor 1, floor 2, floor 3, between floors, then you use vias. So if I have a metal 1 routing this way, I have metal 2 going this way, but I want a connection at here, then I put a via at here. So you can do this, you do these things, but many times is that if you are doing minimum size transistors, your gate poly and the active, so then this overlapped area is your active transistor. So that's where your transistor. The overlapped area is the most critical area that forms your transistor. So now in this one, if you do a minimum size, then the gate poly width is so small that you may not even have enough area to put a contact in it. So then what you do is that let's see. No, it does not have one. So then you need to do things like this to go. So if this is your, let's see, it's like this. So this is your poly, and then this is let's see, this is D and S, drain and source. Now this is so thin, if you put a context here, it may not be large enough. So then what you can do is you can make it wide like this, so that you can put a context there. So this is the dog bone that we're talking about there. Okay. Now also we said that for this transistor here, this is the critical area that forms your transistor. And then you never want to put any contacts right on top of the transistor, because that's the most critical place. You don't want to put your contacts right on top of this, okay, on top of the poly to connect to metal 1. So then your metal 1 here can go other places. So this is being talked about on this place. So then this is no, you don't do this. So this is your transistor. So this intersection here is what it defines your transistor. So that's the most critical area. You want to protect it. Okay. So if you want to connect to the gate, then you go extend the poly to the side, and then you put your gate connection to the side. And for the drain source connection, you put it in the drain and in the source. So don't do anything directly on top of the gate. So this side view is that side view, and then this will be bad. So that underneath here you have the gate oxide. Gate oxide is very thin. Okay, it's a very, very thin layer, and if you try to dig a hole here, put your metal connection here, you may damage the area right below the gate area. So don't do this. So the right way to do it is like the right side. I see that almost done. Just one. Somebody was in my office asking about drawing this, the stick diagrams. So I told him that one good habit to have is that you don't use long poly wires as a rule of thumb. It does not violate the DRC rules, but don't use poly to route signals. This is rule of thumb number one. Don't use poly to route signals. Okay, only use your poly near the gate. And when you want to send the signal to somewhere, use metal to route the signals. And then this is one habit you want to form. Another habit that you want to form is that when you have multiple metals, then you can make your odd numbered metals in one direction. For example, metal 1, metal 3, metal 5, they all go horizontally. And then metal 2, metal 4, metal 6 all go vertically. So if you form this habit, again, you don't have to do this one. But if you form this habit, it can avoid a lot of congestion and the accidental connections, etc. On your stick diagram, same material can never cross it. So I saw some students have a metal one going this one, there is another metal one going there, just like when you draw your circuit in 2-1. But if you do it, metal one going this way, another metal line going this way, then they are connected. Okay, they are automatically connected because they are in the same layer. So the same layer material can never touch each other. But different layer you can. Just like we said, metal 1 is your first floor going this way, metal 2 is on the second floor. If the top view, if they overlap each other, no problem, because they are vertically separated. So this is just a passing comment.